Hello and welcome to another episode of Minitab doing some statistics in Express Edition. So as you can see, I've got the Chapter 11 notes, Minitab HT, that stands for Hypothesis Testing. This document is a little bit older, not that that matters, and it has the wrong number on it because that's not the number of your class. Woohoo! But it still will serve our purposes for what we're going to get up to today. I just realized that I need to adjust this a little. That's better. And make these snap. Oh well, I'm going to not be able to edit that out because I did it kind of seamlessly. Too late now. Anyway, so this document will appear right above this video along with the data that I have open over here, which has over 10,000 lines in it. Or wait, no, exactly 10,000 lines in it because that's the limit of the Minitab Express. We're going to treat this as our population throughout this. Now, normally you would not have access to your population, which is totally the purpose behind doing inference and in particular hypothesis testing or doing confidence intervals. So, usually don't have access to the population. We're going to pretend this is our population for now. And as you can see, the information we know about them is their age, which is quantitative, and we have all these ages in years. And since it's quantitative data, we can't be doing proportion testing on it, because proportion testing really should be only applied to things that have two options, a success and a failure. And therefore you can make a proportion out of it, which is just a success out of total. Anyway, let's look at what we're going to actually calculate here. So you have heard someone claim that the average age of the people in the population is 45, but you suspect it's actually higher. So we're going to select a random sample of people and then follow the steps below to find the hypothesis test to figure out if the average is indeed 45 or higher as you suspect. So the first thing I'm going to do is I'm going to create a random sample. So I'm going to go to data. So we're going to go to data and then sample from columns. It's going to ask you where you want to take your sample from first, which if nothing shows up on the left-hand box, remember you must click into the box to get it to show up. So go ahead and throw age in there. It's going to ask you the number of rows you want to have in each of your samples. Well, I want a sample of size 30, so I'm going to select 30. In general, when we sample without replacement, which means an individual, once they're selected from the sample, they are not placed back into the population to be selected again. The reason you want to do this is you want to make sure your sample has independent individuals in it. If you don't do that, they will not be independent. Then I ask you this completely random thing about which base number you want for your number generation. This is a thing with computer science that you can totally ignore and you don't need here. So let's go ahead and hit OK. Yay! And it labels it for you, which is one of the advantages of Minitab Express. It reminds you, hey, this is a sample. I'm going to change the name anyway, because I like to keep note of what size my sample is, so I just got to throw the size in there somewhere. So now mine is sample 30 age, which sounds really backwards. Usually I put it sample age and then 30. So like my sample is of the age column and there's 30 of them, just to keep track of things. Cool. So the next thing I need to ask myself is, what is my null and my alternative hypotheses? So in particular, it's ho-ha time. Usually I have this formatted ahead of time, so that's probably really boring to watch. I tend to do my alternative hypothesis first because it's usually the one you're investigating and the easiest one to spot, or the one you suspect might be happening. It's your reasonable investigation thing that you're up to. Remember, the hoe is boring. She's the thing that is just saying this is what is happening and what your default is and what you need to start so that you can actually do some inference. And so since you suspect the age is actually higher, your ha is going to be that you think it's greater than 45 years. So here's how I'm going to write this, and you might not like this. I'm going to say mean age greater than 45. Ooh. I did it again, years. So there's a couple things I'm doing here. Is I'm marking that I'm doing a mean. I'm marking what variable I'm doing it of. So I'm saying like, that's what I'm up to. And then I'm also marking my units. And the reason I always include my units when it comes to my null and alternative hypotheses is if you can't find the units, this is not a mean test. You shouldn't be doing this. So, just keep data type in mind as you proceed. My mouse is screwing up. Sorry about that. So the other thing about this is you can read it as a sentence. The mean age is greater than 45 years. Or 45 year. That's weird. I should definitely write years. Okay, and then the hoe, she's the boring one. She's the statement that nothing's going on. Hey, I think the mean age is 45 years, or 42, because that's how my typing skills are going today. This is what I think is happening. It's boring because it's not that interesting. It's what's going on. It's just like when you're trying to have a discussion with somebody on what you think might be happening, and they're like, no, it's this. This is it, done. That's not how you have a discussion. It doesn't lead to anything. It's just they're very set in their opinion. Don't be them. Whatever. So the next thing up is we need to calculate the p-value. How you get the p-value is we're going to use Minitab to calculate our p-value. So now that I have a sample, I can build a sampling distribution. And once you have a sampling distribution, you can actually do inference and get p-values. So we're going to click on the statistics button, rather unsurprising. And then we're going to click on the inference button. Now, if you have your menu open a little bit wider than mine, you might see the option of one sample, two sample, resample instead. We would want one sample then. So just so you know, if you've got it smaller, it'll slump itself into inference. And then when you hit it, it'll give you options. Do you want one sample, two sample, or resample? But if you have it a little wider than what I've got, there's that one sample button. And you'll see at the very bottom is your very familiar proportion one. We actually want to do a t-test because that's the test for means. Notice there's the symbol for mean right there with it. The t-test is the most popular and most common test in all of statistics. When in doubt, try to tee it up, yo. I sound so cool. No, I don't. It is what it is. Occasionally you'll be able to use the z-test. The z-test in general is only used if you actually know the standard deviation of the population, but as we know, figuring out values for the entire population is pretty rare. So this test is not used as much. Usually when you're going to do statistics on real data, you'll end up using the t-test. So it's just the one that ends up getting used the most. Alrighty, and you really should only do your tests on samples, so I'm going to throw a sample in there. So there's my sample, I'm throwing it in. Remember, if nothing shows up over here, click into the box. And I'm going to check this box which says perform hypothesis test because I actually am performing a hypothesis test. And I'm going to throw my hypothesized mean in there. So that's the value I think it is, the value that I'm hypothesizing it is. That's from my hoe. And then we're going to hit our options button because you could always check your options. And then it's going to ask you what's your alternative hypothesis, and it says my mean is not equal to the hypothesized value. Remember, you put the hypothesized value in the last tab, and that was 45. We actually don't have that for alternative. Our alternative is a greater than, so we want to change it to be a greater than. Confidence level doesn't matter because we are, doing a hypothesis test. If you were doing a confidence interval, it would matter. And then I'm just going to look at the display options just so you can see what they are. And it's going to ask you, do you want to also graph your data, which you don't have to do. It's sometimes nice to include the interval plot. I'm not going to do that this time just because I want you to see what this looks like. As is, because this is all you need to do a hypothesis test. So just to review, throw sample age 30 into the sample. Make sure you have your hypothesized value coming off your hoe in your box. Don't forget to check this or else you won't be able to type anything in there. Make sure you check your options to make sure the alternative hypothesis matches your alternative hypothesis. And if you're not building a confidence interval, you don't care what the confidence level is. Let's hit OK. Yay! So this first stuff it brings up is not really useful. The only thing in here you might care about is the SE for the mean. That's the standard deviation of the sampling distribution. It's irrelevant. It also gives you like the mean of the sample, how big was the size. If you accidentally made yours too big, now you'd know. And the standard deviation of that sample too. So ignore this lower bound for mean. That's not relevant for what you're up to. All right, here's the stuff I do need. So notice that it states your null and alternative hypothesis for you symbolically. Always double check this to make sure it matches what you have, because if you've made a mistake and one of these is wrong, or one of these looks different from what you originally suspected is for your answer for the problem, then the whole thing's wrong and you need to redo it, just so you know. Then it gives you our t-value. This is your test statistic. That's 4. Wow, that's huge. 4.1. That's more than 3 standard deviations away from the mean. Oh, that's pretty big. Or more than 4 standard deviations away from what you suspected the mean was. So that's very unusual. So your sample was unusual compared to what you suspected was happening with your null hypothesis. And so there's your p-value. Let's go ahead and type that in since that's asked for in this problem. How many zeros? 3? Okay, good. Cool. Now I need to state my conclusion. Well, that p is tiny. So we are definitely going to be rejecting our null hypothesis. It appears that my sample data does not agree with that null because notice it's pointing towards this is a very unusual sample to get if that null were true. So it doesn't look like our evidence supports that. So I want to say that in my sentence. So I want to say the evidence suggests that the mean age of these individuals, I don't know what they are. If I had more data, here is where I'd say it. If I knew they were like salespeople or something, or maybe they were my customers. Mean age of these individuals is, greater than 45 years old. And I usually report my p-value. This is not a requirement, and not everyone does this, but I do because it means that if someone else goes and wants to check my work, they now have what my results were. Maybe it was, different from what they expected. So I like to include this. If you end up taking stats too, you'll do this on everything. With a p-value of 0.002. Also, my p-value is super tiny, so it's kind of like a slap in the face. It's a lot of evidence that this is just what's going on. It's so small. Please remember the p-value is a probability. So what else do I want to say about this? That's probably good enough. So just be careful with this. When you're stating your conclusion, it should actually answer the question. You've heard someone claim that it's, 45, but it's not. It's clearly older. And the other thing to keep in mind is when you look at this, when you're making your decision, your p-value, you should be comparing it to your significance level, your alpha. And if your p-value is small, that's where your cutoff for small is. Is it this big or bigger? Is it this or smaller? Smaller than this, it's small, and therefore it's definitely not something that you should likely have happen on the first sample you took from that population if the mean was actually 45 years. Yep. Cool. So now we're going to repeat all of that, but we're going to use a random sample of 150 people. So you're going to see me go through all these exact same steps again. So I'm using the same null, the same alternative hypothesis, but I'm just going to be using a different sample. So I'm going to go back to data, sample from columns. I still want to do this to age, but now I want 150 people. Still sampling without replacement. Don't need a random seed. Go ahead and hit OK. And this is why I really wanted to make sure that we were clear about who was the size 30 and who was the size, just to keep them apart, because it names them the same thing, and that can get a little confusing if you don't label them. Anyway, so now I've got a sample of 150. Notice this is a bigger sample, so it should have less variability in it and should be more consistent and look more like the population, ideally. Because as we've seen, the best thing you can do to reduce error is take a bigger sample. So I'm hoping this is going to be more accurate than my previous results. But they might agree, because that's a pretty tiny p-value. Let's find out. So we're going to go back to statistics, one sample or inference, and then one sample. Select T. I'm going to throw my new sample in there, my 150 sample. I'm still doing the same hypothesis test, so I got to check that and make it 45 as my hypothesized mean. Go to my options, change it to a greater than, still 45. For funsies, I'm going to show the display for the individual plot value, just so you can see what it'll look like. It's not that interesting. So again, that last thing I did was show the individual value plot, just in case you wanted to see what one of these looks like. We don't really do the other two. We sometimes will do the histograms for the 2 sample tests, but we don't really do that for 1 sample test. Let's go ahead and hit OK. All right, so let's look at what we got. So there's my sample size. There's my mean, bigger. But remember, just because the sample has a bigger mean doesn't mean it's a statistically significantly bigger one. It might be that with their spread, these are really close. The spread is about 9. So again, that's not that. So if you're thinking about spread, if the standard deviation is 9. 45 is not 9 away from 5. It's pretty close. But remember, we're doing a sampling distribution, so the standard deviation you should be using is the SE for the mean, not the standard deviation of the sample. That's the stuff from the sample. We're trying to talk about the population. That's the whole point of inference. All right, let's look at what our p-value is. It's so small, Minitab's mad about it. That's what this is saying. It's so tiny that it doesn't show up. It'll just let me give you more values. The plus sign isn't showing up. Hold on. Nope. So typically when it's this small, sorry. I'm clicking on all kinds of things. I hope that wasn't too confusing for you. What you can do is you can actually force Minitab to tell it to you by doing the t distribution. So I'm going to pause this video for a second because I'm going to need to write this value down to make sure I have it. Yeah. Okay, I'm back. It's just that I need it when I go to the next menu and I'm worried I'm going to miss it. So if you're like, that's unhappy, it's so small it looks like nothing, and Minitab won't tell me what it is, I need to know what it is. I'll show you how to get that in just a second. The next thing I want to do is I want to show you how this looks for that plot. Let me make this a little bigger. And then make it show only the output. So as you look at this graph, it's showing what the sample looked like. Notice you got one outlier in there. That's not a good thing. And then it's giving you an interval plot. That's supposed to be a confidence interval that's one-tailed. Not that that matters to you. And then there's it marking what the mean is. So what this is saying is that if you were doing a confidence interval, your mean lies outside the interval, which would tell you that this doesn't look like it's supporting that hoe. Let's turn our data back on, because we don't really need that anymore. And I'm going to show you how to get the p-value for this in case you need it. There's also a couple videos on how to do this, but I might as well do it now. So we're going to go to graphs. Oh, sorry, statistics. I always click the wrong one for this one. We're going to go to distribution plot, display probability. Now we're doing a t here, so I'm going to change this to a t. And it's going to ask you for your degrees of freedom. My sample was size 150, which means I subtract 1, and my degrees of freedom is 49. And then since my alternative hypothesis is a greater than, I know this is going to be a right-tailed test. I'm not doing probability, I'm doing x value. So I'm doing like, is it greater than 45? So greater than is like things bigger than it, which would lie to the right on the number line. So things to the right of that value on the number line. I said that already. Oops. So I'm going to put my t-value in there of 5.33, and this should give me a more detailed result that tells me what that value is, and it's going to be small. Let's go ahead and hit OK. And, oh, I should have left it on date output only so you could see this, because this is how tiny it is. Look at that, it's a 2. That's a coincidence, just so you know. That doesn't always happen. So it's so small, it's like so many zeros before you hit 2. That it's reporting it's less than a millionth, so it looks like nothing. And that's why when we did the 2 sample t, it's like, it's so tiny it doesn't matter, and you're not going to tell me it's any different from what we're seeing. So what you're saying is, I did a sample and I got something that was so unlikely it looks like it shouldn't happen at all. It's probability 0. So the evidence is super saying that it's not 45. So once again, the evidence suggests that the mean age of these individuals, I don't like that. You should be saying something more specific, like these penguins or these elephants or these sales managers, and something, not individuals, is greater than 45 years old. And I'm not going to report the p-value here just because I don't feel like trying to type all those zeros. Maybe I should, though. Let's do it. Because it's kind of like so small. Everyone needs to know. 0 point, how many zeros? So many. 1, 2, 3, 4, 5, 6. Oh, that's so small. Oops, I forgot my width. And I burped. That's gross. Notice this is a capital P for probability, yo. It's not a little p, it's not a proportion. So that's about it. So this is where you should also get mad with hypothesis testing. They're like, it's greater than 45. So you should look at me and be like, well, what is it then? Is it 60? Is it 46? Is it 9? Is it 3? Oh, those aren't bigger than 45. And that's really the downside to doing hypothesis testing. They really only test, is that claim reasonable? Do I have evidence that supports it or not? It doesn't tell you an estimate for what the mean actually is. Only a confidence interval can do that. That's what we're going to do next. So we're going to go back. I'm going to turn my data back on. Turning the data on. Doing stats. And we're going to do a confidence interval for the 98% level of confidence for the 150 people sample. So we're going to go to statistics, 1 sample, and then over to the t. All right, it's going to ask you where your sample is. Throw in sample age. It's going to ask you, are you performing a hypothesis test? I am not. I am doing a confidence interval. So I'm not checking that box. I'm not putting anything in there. Do not do this if you're not performing a hypothesis test. If you're just doing confidence interval, do not put anything in here. You will definitely get wrong results if you do. We're going to hit options. And then we always leave this as a not equal to for the alternative hypothesis, because otherwise it gives you a one-sided confidence interval, like that weird graph I showed you earlier. Don't worry about those. No one does them. All right. So now we need to tell it its confidence level. And 98 is not an option. Huh. All right, well, I'm going to do 99. I'll show you how to do the 98 one in a second. Alrighty. So just as a review, we put the sample in. No hypothesis testy. Make sure you're not equal to, and you've got your confidence level in there. I really thought it did 98, but evidently it doesn't. I'll show you how to do that one by hand. Let's go ahead and hit OK. And there's your confidence interval for the mean. Right there at the end. None of this stuff matters, just that. So I'm going to type something just because I want to make sure that this is clear. The 99% confidence interval is 47.1551, comma 51.2849. It's worthwhile for me to mention at this point that if you are following along with me, you probably have a different confidence interval than I do right now because we all have different samples because it's random. You can't see me right now, but I'm trying to make a rainbow with my hands. It's not really working. Magic? No, math. Remember, everything's random, yo. So, I need to stop saying yo. Anyway, that's not an interpretation of the confidence interval. That's just me stating this is what it is. That's not the same as saying what it actually means. So to write interpretation, I need to actually write what it means. We are 99% confident, that the proportion, this is not a proportion. Oh my god, I'm going to start this over again. It's not an interpretation. Here's an interpretation. We are 99% confident that the mean age of the population is between 47.151, oops, I missed a 5, and 51.2849 years. Done. That's what it tells us. Ah, it's bigger than 45. What could it be? Somewhere between 47 and 51. That's not too big of a stretch of age range. It's only about 4 years, so that's not too far off. So here's the thing. How do you do a 98%er? So remember, to do a confidence interval, you need two things. You need the estimate, plus or minus the margin of error, which is the same thing as taking the estimate, plus or minus your z or t value, in our case it's going to be t, times the standard error. And the reason I got lazy and did the 98 first is because this does a lot of the work for me. So now I want to get the 98er. I have an estimate. That's the mean of the sample, which is that 49.22 plus or minus. I'm writing that terribly because I don't want to look up the symbol for it. So plus, minus. Now I need my t-value, which isn't on here, so I'm just going to leave a space for it. And then I'm going to grab my standard error, which the standard error is the standard error for the mean, which is right there. So see why I did the interval first, using the 99%er, because it gives me everything I need with like one step. And then the only thing it doesn't have on there is the t. So the t I have to get from doing that, I have 98% in the middle, or 2% in the tails, on the t distribution with a degree of freedom of 149. So we're going to do that right now. So we're going to go to distribution plot, display probability, change this to a t. I did that kind of fast. So distribution plot, view probability. Chapter 7, yo. Go to t. I have 149 as my degrees of freedom because remember it's 1 minus your sample size. Here actually I'm going to specify probability because I want 98% in the middle, or I want both my tails to have leftover 2% because that's what's not in the middle, 98%. I tend to use equal tails for this. Let's go ahead and hit OK, and that will give me my t-value. Doesn't matter which one you grab. You can grab the negative one, you can grab the positive one. Since you're doing plus or minus, it doesn't matter which one you use. And I'm probably going to round mine. So I'm going to do 2.3, I don't know, 5.2. That's probably good enough because these are 3 or 4 decimal. Actually, they're 4 decimal places. Let's do 4. Let's keep it consistent. All right, so then I'm going to do 49.22 plus or minus, and you cannot see me doing this, but I'm grabbing out a calculator and multiplying those two together. So stalling. Oh my god, that's the most interesting thing I've ever done. I should have did it on screen. 8611-ish. So then to get the upper interval, I'm going to end of the interval I'm going to add, and to get the lower end of the interval I'm going to subtract. So I'm going to take 49.22 and subtract 1.8611, and that'll give me 47.3589. Me yelling numbers is so interesting. And then I'm going to add them together, so I'm going to do 49.22 plus the 186611, which I'm rounding a couple places here, so you recognize this will have some error in it. Ta-da! Ooh, I missed my decimal. Very unclear. So notice this is a different interval than the one above, and it is a narrower interval, which you should suspect because as you look at this graph up above, this is 98%, 99% would be even further out, which would mean a wider interval. So like probably from here to here, rather than from here to here, which would make your t-value be further away or larger, and that would make your margin of error larger, and therefore your interval wider. Fun facts. Okay, so now we're going to play a game. Hey, here's the thing you normally can't do. And it's also a good memory. Number 5. Find the true age of the population. Why am I going to do this? Because I want to see how accurate I was. Up earlier I said, hey, it's got to be bigger than 45. I did it twice and really confirmed that that's what's going on. Then I was like, hey, it's somewhere between here and here. Let's see if we manage to get it. Now keep in mind as you do this, 99%, 98%, there's a 1% chance of failure. There's a 2% chance of failure. So that means that for the 99% interval, 1 out of 100 of you is going to get something as you do this sampling that just doesn't agree with what the truth is. And then 2 out of 100 of you, or 1 out of 50, will have it happen for the 98%er. So let's see how we be. So this is kind of fun because the very first thing, well, not the very first thing. Yeah. Well, no, wait, no, we do chapter 2 first, which is categorical variables. In chapter 3 is when you learn about how to do a mean. So I'm going to find a mean, which is like the second or third thing I teach you on how to do on Minitab. So this is like a trip down memory lane, just in time for the class to end. So we're going to go to statistics describe, and we're going to go to descriptive statistics. And it's going to ask you, oh, is your data all in one column? Yes, it is. My variable is age, and I'm not going to do grouping because you don't need to group this. There's just one variable. I want to find the true age. I want to find the mean. So the oh my gosh, the statistic I want is the mean. So I'm going to turn all of this stuff off. Oh, it's like memories, love, things. Good times. Great math. Let's hit OK. I'm getting a little depressed because it's the end of the class. It's 50.1528 is the true age. So the population age is 50.1528 years. And hey, it's bigger than 45, isn't it? So my hypothesis test was on the right track. And in particular, notice both my intervals. No. 50's in there, isn't it? Oh yeah. Well, 50.1528. 50.15. Oh, they were both successful, so I didn't fail this time. How great. Darn. One of these years I'm going to get real smart and tweak my samples before it... Oh, that seems very dishonest. Beforehand, so I can have one of them screw up. But it could happen to you. You could get something that doesn't make sense as your conclusion. This is the part where predicting runs into some rough times and may not be as accurate as what you hope, because there's going to be a failure rate for this. You're trying to look into the future. Don't think crystal balls or anything crazy like that. You're trying to make predictions. And remember, there's always a chance of failing when it comes to making predictions. You just got to do the best you can and not say more than what you know. Try that in your real life too. Don't say more than what you actually know. Ending on advice this time.